Hello, hello. This is the second episode of Poincare's Insights, and we have a guest here today. His name's Will Templeton. Will Templeton, third year, Cambridge, and my co-host Dylan Shaw as well. If Will wants to introduce himself anymore, he can.
Yeah, sure. I'm Will, third year maths student at Cambridge. I mainly am studying courses in physics and mathematical analysis, which I might talk a bit about later. Within the university itself, I'm president of the Maths Society as well, so I run lots of events regarding bringing mathematicians in to talk about their ideas and stuff like that. So yeah, whatever questions you have, I'm happy to answer.
Yeah, we'll go for it. Uh, well, I guess the first question I have is, what different mathematicians did you look up to when you were younger? Like, obviously, when you had interest in maths.
Sure. So I think it's quite common for a lot of people on my course to have a set of mathematicians they love when they were like a child. People like Andrew Wiles or Euler. And then actually, as you get more technical into different fields, those people change and they become, I think, a lot more human in that process. So I think when I was a lot younger, people like Andrew Wiles, I loved the documentary about his work for Maslow's theorem and the book. And the fact he spent so long on a problem independently was quite amazing. And but the more I've learned, I think those sets of people have changed. I'd say now I really respect the work of a guy called Ed Witten, who you've both may have heard of, probably not in comparison. Um, Someone like Richard Feynman, I used to absolutely adore as well. But you just sort of grow, discover new ideas, discover who thought of them at first, and definitely one thing's for sure is that there's lots of personalities in the mathematical world, and very different people.
That's cool. That's cool to hear.
Nice. Did you say you were taking like physics modules as well?
Yeah, so
So,
the Cambridge maths course is quite unique in that you can basically do a physics degree as part of it. For instance, this year, the majority of my modules are physics based. So I'm doing stuff like cosmology, dynamics, quantum mechanics, and that sort of stuff. So really, it depends what you're interested in, but the Cambridge course is particularly broad. And I think that's a good thing because maths is not an area where you can't really pin it down to any one thing. Like the applications of maths to say physics or computer science or other areas are so like vast that to say that a maths degree should be about just pure maths or number theory and stuff would be quite limiting. So I think it's a good thing for degrees to be very broad in that sense.
so I'm guessing you see like a lot of overlap between like physics modules and like your current maths degree and all of that.
Yeah, I'd say so. So the lines are actually a lot more blurred than people would imagine. So even though at the minute I'm also taking courses in areas of pure maths that are very pure, an area of maths called functional analysis, even within that and those areas, there are quite deep connections to ideas in physics. And there's this constant race going on between maths and physics about which ideas come first. For instance, do new ideas in maths motivate physical models of the world, or do these new ideas about how the universe works motivate mathematics that's never been done before? And actually, the answer is both of those are true. So people shouldn't really say that physics and maths are separate disciplines because without both, they wouldn't be as broad as they are or as deep as they are.
That's cool. I guess like the next question would be, where do you think the limit of maths itself like lies, or do you think there's even a limit? Like obviously linking with physics and everything. Like I guess you cover lots of stuff with like cosmology, like the universe itself. I'm just like wondering where the limit lies for all of that.
So I think a good question to ask is, are there any problems in maths that can't be solved? And that's quite a good starting point to have. And I think actually that there may well be problems that can't be solved. You may have both heard of the Goldbach conjecture,
Yeah,
Mm.
which is quite a simple statement, but I think a lot of people suspect that it can't be proven or will never be proven because there would never be a nice enough argument. I'm just going to put my laptop on charge quickly. Sorry. um, It says it's going to shut down.
That's cool.
I think in terms of how maths is applied to the world is a different question. So in terms of arbitrary questions in pure maths, I think there will be questions that you can construct that are extremely difficult to solve and may never be solved. I think in that sense, you can imagine asking a series of questions which just become more and more complex in time, and answering all of those becomes increasingly challenging. It increasingly requires ingenuity, and I think that there will be a time where just new mathematical ideas and problems will just become too complex. On the flip side, I think in terms of applying maths to the real world, as I say, there's sort of two directions to that. There's this inwards direction, which is about how do you come up with those underlying theories that describe the world well. I think actually in terms of that, maths will provide quite a strong answer in our lifetimes. The only question is who's going to discover it. But on the flip side, you start with these like physical laws, and going from that to really complicated systems such as things like fluid flow or the aerodynamics of a plane. That's a different question in a completely different respect. That's where it becomes too computationally demanding to work out how all these particles interact will produce, say, a force on an object. I think that there is definitely a limit to maths, and the limit then becomes about sort of algorithms, computational complexity. And I think depending on advances in those sorts of areas, modeling, complexity, particularly computational, that there may be some limit to what systems we can model mathematically. So I think someone was awarded a prize within the last 3 or 4 years for modeling the thermodynamics of a cup of tea or something like that, which seems like quite an insignificant thing. But considering all the different parts of that, the pressure, the temperature, and all of it together, required a lot of computational power. So I don't know whether something like quantum computation will realistically change that, or machine learning and stuff. But if it doesn't have the power to, I think maths can increasingly model lots of the things in our daily lives.
Yeah, that kind of like links to my next question. I was gonna ask. Wait, what was the question? It was um oh yeah, what impact do you think like maths will have in our future development? Like, do you think maths is quite important for our future like development and like all of that?
As in like
Like
how?
as in to move forward in society, like real world development.
Yeah, so I think we've seen the start of this in the 20th century. So this is what's different to history, is that information technology, computers, machine learning have come to like revolutionize our lives completely. All of this is based on logic and on maths. I think before then, like obviously maths had applications, but maybe to how you'd fire a catapult or something like that. There were no sort of incredible ways in which maths revolutionized people's lives. Now it's different. If you look at machine learning, all of that is based on relatively simple mathematical ideas, and people are just put all their effort into researching these and developing these algorithms. I think that can only increase. And then the question is, how are these applications going to change our lives? So take something like machine learning. I think overall it would be a positive thing, but I don't know, it introduces all sorts of ethical problems, and there's a growing worry about the ethics within maths itself, because is it driving change that perhaps people don't want? So people obviously, when say the atomic bomb was developed, thought, has physics overstepped the line? Have they gone too far in discovering and building something that actually has negative societal consequences? I think people are increasingly starting to ask those questions in sort of the mathematical world because of machine learning. What happens if some malevolent person used this maths and machine learning to produce something that could have negative consequences, and those sorts of questions. So I think that it's an important question to ask more than ever is about how maths is changing the world, precisely because in the past it has, but in ways which weren't as significant to someone that doesn't study maths, obviously.
That's cool. I guess like an underlying question of all of this that we didn't ask was, what attracted you to maths at like the start? Like, what made you study maths, and what interests you further to obviously research machine learning and everything else?
Sure. So I think, and you both probably in a similar boat, that loads of people go to study maths because they think it's something they're good at in school and they think it will be relatively okay at degree, and that obviously there's lots of well-paid jobs involved afterwards as well, if that's what you wanted.
Yeah,
I think when people start their degree, they realize actually this is quite difficult. And so lots of people in their sort of first year of studies have a moment where they actually have to reflect properly, why did I study this subject, beyond just say what they wrote in an application sort of thing. I think for me, I always did like the logic behind it. Like I never used to like just sort of memorizing facts or understanding something without being able to ask questions. And I think even in like a GCSE science lesson, there are lots of questions you can ask that will completely stump the teacher, that there will just be no sort of good explanation for. I think the system in maths of having all the logic laid out, all the assumptions laid out, and all the consequences and applications are visible of that, I think is quite a satisfying thing for if you're logically minded. And I didn't have this before university, but since you start to gain an appreciation of what it means for an argument to be particularly nice as well. There's some special property that if an argument is just nice, you have this feeling about it that you've used a bit of ingenuity or a bit of cleverness to come up with an idea, which it probably started just being something you had a little intuition about, that you were able to make precise using notation and so forth. And it's a really nice feeling to be able to turn something that's just like a gut feeling into something written on paper that's correct. And the more you do that and the more practice you have at that, it's not a particularly useful skill outside of maths, but it's a fun one to develop.
Yeah, yeah, I completely agree. I mean, like the subtle like paradoxes or contradictions in maths, they like really keep me up at night. They just like it's it's like a sense of when you don't know the answer to something, or like you really try and figure something out, you have this drive to just feel your curiosity, just like learn. And I guess that's what drives my motivation to learn maths, because I like the little problems in it and the satisfaction that comes with like solving a hard question as well. It's like
Exactly.
it's really nice. So yeah.
Yeah. So like the way a course is usually structured at university starts off with just maybe like 3 or 4 quite simple assumptions. So let's say like number theory, it will just start with 4 assumptions being like two numbers can add together, two numbers can multiply together, and things that you don't really have to think about. And then it will just take those ideas and run with them and develop all sorts of structure and ideas which all relate to one another in a really nice way. And it does make you think how it's sort of the miracle, if you like, is that you can start with a set of relatively simple, maybe abstract assumptions, and then derive quite powerful results from that. And it just feels like, where is all this coming from? I've just written down maybe 3 or 4 assumptions, and all that follows are these really nice ideas and theorems that all link together. And it's a question people always ask themselves is, how does it just happen? Like, how can this follow? Like, you can really easily define the natural numbers, right? You just say, let's start with number 1, and then let's say, given a number, +1 exists. So you have number 1, you have number 2, number 3, number 4. In a set of axioms called the piano axioms. And then given all that, you have all this structure with things like prime numbers and stuff like that, that all just seems to appear from these underlying set of assumptions. So it really is the one subject that takes a set of ideas, runs with them, unlike, say, other areas of science, which you can't blame them, but they have to start with assumptions that are a lot more jumps in logic. Like for instance, when you first learned the atomic model with nucleuses, electrons, protons, neutrons, like I don't know, for me, I just see something like that and I just ask, where has this come from? Why do we just assume this? It seems like quite a big jump from understanding the world as we see it to introducing this whole new idea. And obviously you can understand the experimental evidence for these things, but just to have that jump in logic that let these things exist, doesn't sit well with someone that's sort of naturally mathematical, I guess.
Yeah, that's really cool. Um, the next question I had was, what's an interesting idea or problem like you come across recently? Like I know we talk about like lots of stuff in our lessons together. We talk about like group theory. We've come across different like Stirling's approximations. I remember different like complete ideas. But what's the interesting idea you found?
Okay, so there's a really nice idea in theoretical physics, which isn't too hard to understand. You'll probably learn about it in some way or another in first or second year, which relates the idea of symmetries to conservation laws. So it's called Noether's theorem. It's named after trailblazing female mathematician called Emmy Noether. And the idea is you can derive with not too much sort of complicated algebra that given you start off with some symmetry in the universe, and what I mean by that is things that don't make a difference. So for instance, if you moved everything in the universe 1 meter up, everything would there'll be no change. If you started a stopwatch and moved it a minute forward everywhere in the universe, i.e. just skipped a minute, but everything else was left the same, nothing would change. And you call these sorts of things that you can apply to something, and it doesn't change its symmetry. In the same way that if you have like a symmetric shape and you do a reflection or rotation, it stays the same. Changes you can make which don't result in any visible or real change to the system. And it turns out by these properties of you can move everything in the universe 1 meter to the left, 1 meter to the right, or rotate everything a certain number of degrees, you can derive directly from that you have conservation laws. Things like conservation of momentum follows directly from this idea that everything in the universe is invariant under those sorts of symmetries. So it's a really nice idea. And in sort of the first and second year, you use these ideas to derive conservation of momentum, conservation of angular momentum, even conservation of energy follows from these fundamental ideas that the universe is symmetrical in these ways. And actually, current theoretical physicists use their best guess at symmetries to derive, actually, this is how the standard model works, this is how electrodynamics works, this is how general relativity works. So really, it was this idea that symmetry is at the heart of modern theoretical physics is quite a nice idea, I think. And it's one that you're introduced to relatively early on, and it would just build and build and build on it.
Yeah, that's really cool. As in, like, we both do further maths and physics, so like we've both
Yeah,
done in lines as well, and we both done obviously just like physics in general. And like this, we've never really thought about like the links between symmetry and conservation laws. I think that's
Exactly, yeah.
yeah,
So it turns out most principles in physics you can relate to in one way or another quite a simple mathematical idea, which is why I think the two subjects should be studied sort of hand in hand. You can't really separate them. It's because you then no longer have appreciation for these really cool ideas, I think.
nice, nice. Um, well, I was thinking about this the other day. I don't know if it relates too much to this, but I, I I'm not sure if they like if you've come across this at uni or if they might have given it to you as a brain teaser, but I was just thinking about how you cannot divide by zero, and I'm not sure if you have the answer to that, but yeah, I know I'm curious to see if you like come across these little things at uni because it seems like a little icebreaker or like a little puzzle like someone would give as a starter. So yeah,
Sure. Yeah. So I think
I've never thought about that as well. It's kind of interesting.
yeah, my brain just works differently. I just think about these little like stupid things which are like irrelevant, but yeah,
no, it's a good point, and I think it's all about how you define things at the most fundamental way. So why should we be allowed to divide any two numbers together? It's because we just define what division is, right? We say let division be this property, which is the inverse of multiplication, which means that if division is the inverse of multiplication, then there cannot be a way to divide by zero because zero has no inverse. And so it's all about defining these things in a set way, which I mean, I guess you could say is sort of taken to be mathematically convenient and for the purpose of what we want to do. And it seems like a bit of a get out, but we can just say division by zero is just not a thing. It doesn't exist. Um, it's not in the definition of what it means to divide two numbers.
Mm,
Uh, I guess you could then also say, well, what if I have the function 1 over x? And you could ask, okay, well, what happens as I draw this graph as you get closer to zero? And those things are better understood by an area of maths called analysis, where you can start to look at these singularities, as you'd call them, where you divide by zero, and you start to be able to find ways of treating these things carefully. Um, I think 1 over x is pretty well understood, but there are others which are more complicated.
yeah, I've always thought of it like that, like 1 over x, because if you like keep on dividing by a smaller and smaller number, it'll get larger and larger and larger to the point where it's like undefined. So yeah,
Exactly.
that's how I thought of it.
Yeah. So
So yeah.
for that sort of situation, we would define that series sequence, sorry, as diverging, meaning that it reaches no sensible
Mm.
limit. It just tends to a larger and larger value. And I know it's nice to have precise answers, but you just have to leave it at that. You can say it tends to some large number and then don't ask any more questions is essentially the way we do it.
Yeah.
Fair enough. Well, obviously, like you're doing your third year at uni currently at Cambridge. What's your plans like after uni with the maths degree?
My plans, so they they're dependent on a lot of things. So in Cambridge, there's part three, which is a master's course, which is a very prestigious course for people that do well in the first 3 years. Results contingent, I hope to do that. Otherwise, I might move to astrophysics as a master's degree. And after that, probably a job in finance, unless I did particularly well in the master's, in which case, hopefully research. But so there's lots of different potential routes. And it is a very employable degree. And it is a degree where I hear that people that do research really enjoy it as well. So there are lots of routes open to you with a master's degree, and all of them are pretty decent.
Yeah.
Nice.
As in, when you talk about research, like, what are you technically doing? Like, are you trying to solve like the Riemann hypothesis or something? Like,
Yeah,
interesting.
so I think a lot of people have an idea of mathematical research. Um, and I think it's really different depending on the person. So like someone that doesn't know anything about maths thinks that a mathematician sits in his rooms doing more and more complicated sums. Someone that knows a bit more maths might think the same, but more and more complicated formulas. Um, and every year you spend studying maths, your idea of what it means to research changes. I think the best idea I have is that it's not so much pick a problem, let's try and solve it. It's let's have some ideas about one really niche area of maths that you're interested in, read around that area, try and understand everything that's been written about it, and try and find a contribution you can make. So for most people, it's probably more boring and less romantic than say trying to solve the Riemann hypothesis, right? But I think based on these smaller pieces of research that are done in more niche areas, then actually the building blocks are there for people to come along and realize X implies Y, Y implies Z, therefore this problem is true. And that's exactly what happened with Fermat-Sass theorem, is that a guy called Ken Ribbett from the States proved a lemma, which meant that Andrew Wiles could then come along and say, well, your lemma has turned this problem into something which I'm an expert in, so now I think I can solve this problem. So I don't think you rarely get a mathematician saying, I'm going to try and solve one of the millennium problems, right? It tends to be
Mm.
more, it does happen, it has happened, but it tends to be more a niche area.
Yeah.
Nice. Yeah, I have another weird question, but um, how do you think maths is taught around the world? Like, do you think it varies from country to country? And like, even that, how do you think Oh, well, I'm just also curious to know how maths at Cambridge is taught differently than like let's say high school or just other universities in general.
Sure. So I think maths around the world is generally taught well, but it's not taught for people that want to study maths. So
Mm,
maths in school is taught for people that want to become a doctor, an engineer, or someone in IT. So for most jobs, you require some level of numeracy and of solving certain types of equations and stuff. And I think that the education system does do a pretty good job of that. But I think it does do poorly at training people to have the sort of skills required to do maths from a more advanced perspective. I think a lot of changes have been made over the last 20 years or so. I think particularly the introduction of STEP. Um, Obviously, STEP's been a lot older than that, but I think now you have more people taking it than ever and more resources online available to prepare for these things. I think the STEP, MAT, and those sorts of exams prepare people in a much better way for uh, doing actual maths as opposed to the sort of maths you do in school, which is like maybe solving an integral or doing a differential equation, which is important. It's important to be able to do those things, but there's nothing there that would distinguish you from, say, an engineer or a physicist or even, say, someone involved in sort of the biology side of medicine and stuff like that. I also think that the charities like the UKMT do a pretty good job of adding extra challenge to people. Um, I still think there's a long way to go on that. I think the standards of education in private schools when it comes to competition maths it's very unequal at the minute, and I don't think that people from comprehensive backgrounds have the same opportunities in that sense. I think that will change as a lot of this stuff becomes more online. But for the time being, I think it's okay, but could do better. In terms of the second part to your question about Cambridge, I actually think I don't want to get in trouble for saying this, but I think Cambridge does a pretty poor job generally with how it teaches, and I think most people would agree this is because most academics at Cambridge are really strong at research, but not so much perhaps teaching. And there are some
mm,
brilliant lecturers and brilliant supervisors, but I think on the whole part, it's a research-driven university, which means I think actually when I look at people's lecture notes from other universities, that they're better, they're more clear. Uh, so part of that's tradition. Institutions like Oxford or Cambridge are resistant to change. They're resistant to using more cutting edge ideas in education and teaching as opposed to other universities. But I think these things will change eventually. Um, it will just be a matter of time.
mm. I mean, leading on from that question, like, now I want to ask about, do you think the maths that we're learning is enough? So, like, the to the point where we stop learning maths at high school or university, do you think we've learned enough maths to set us up for like our future jobs or just life in general?
So I think so, but I don't think it's ideal. I think particularly in the United Kingdom, this is a services-driven economy, so that means a lot of the money from the UK's economy comes from things like the financial sector and stuff like that. I think
Mm,
given that, there should be a greater emphasis on maths as, say, other countries, just because there are more jobs relating to quantitative and mathematical areas. I think that makes sense. In terms of how fit for purpose the high school curriculum is, I think it's okay. I think there ought to be, rather than forcing everyone to do GCSE maths, there should be a more standardized test just to test basic numeracy skills and stuff like that. So that's to say, not everyone's going to be aiming for a grade 9 in GCSE, but you could have some alternative exam which just says to a business, this person can work with numbers, they can add together or multiply together and stuff like that, because everyone's proficiency with maths and numeracy uh, obviously changes depending on what job they're going to do. And I think the GCSE system probably is insufficient for that.
That's cool. Yeah. I think like probably basically a final question. I think I asked this like first episode podcast as well. It's just like a good question to ask like everyone. Like, do you think maths is discovered or invented, in your opinion? Obviously.
I think now most people have very strong views on this, I think. I would say it depends on the context. So, for instance, like when Newton discovered the law of gravitation, I would use the word discover then because it's a observable law deriving mathematical principles from what you see around you. It's something you discover because it's observational. When it comes to inventing maths, I think there are examples of areas of maths, particularly one called topology, which seems to take something that's natural that we observe, the idea of distance, and generalizes it to the extreme. And I think that's an example of what you could say is like a toolkit invented by mathematicians. Just because it's invented doesn't mean it doesn't have its use. And it turns out these ideas in topology have huge applications to other areas. And it's because of those applications that people may ask, well, if I've invented this really abstract toolkit that turns out to have applications to other problems in real life, then is there some deeper truth to that was there before we just invented it in the first place? And I think for that sort of question, you should ask a philosopher because I couldn't answer that sort of thing.
Fair enough. Fair enough. I just had a random question. It wasn't really planned, this one. It was like, do you need to be like not like net per se a genius in maths? Do you just need to be like really well read in maths? Like, as in, like I used to watch like videos of like geniuses just like going through maths problems, finding it so easy and just like really nice, like going through IMO problems like they were a piece of cake, which is
Yes.
really
Yeah.
hard. And they're like, it's just like me struggling on like random A level questions. It feels like I can't like compare to them in maths. It feels like sometimes you need to be like a genius in maths to just continue further.
I guess you could argue that they've had years of experience. Like
No,
they've been
some
doing
of them are
maths
like
their whole life.
14. They're younger than me. That's the problem.
Oh, well, well, I don't know. They're just built different.
So there definitely are those people, and they are exceptional. And every time I meet one of them, I'm always amazed by what they're able to do. The question is, do you need to be like that to study maths or to make any sort of progress if you want to do research? And the answer to that is a definite no. So there are lots of people that never touch, say, an Olympiad in their life that have very, very successful careers as mathematicians. And even on sort of the converse to that, there are examples of people that were extremely strong in things like the IMO, that did really well in say solving problems at university, but then couldn't really do research. And the reason is because these skills are so separate. The idea of working on a problem for a long period of time where you're not guaranteed to make progress or guaranteed there to be a nice trick is very different to solving a say IMO problem where yes, there might be a few tricks needed to solve the problem, but actually once you have someone that's got those sorts of experiences and the sort of practice and thought process required could solve it within, say, a few hours. So I think the nature of the problems is very different. And even for people that have done well in Olympiads and stuff, university maths is not easy because it is just a different flavor. It's a different style. I think generally there is a huge problem in maths with people comparing themselves to others. And it's obviously an easy subject to do that in for what might take me a while to understand something someone else might do quickly and vice versa. And a lot of people end up thinking that they're worse or better than others. I think overall it's not a healthy approach to have. It's just I get the chance to study these ideas, to do this stuff, and you really shouldn't worry about how other people do in comparison because I think overall it's a counterproductive mindset to have.
Good. I've definitely had that mindset a few times in my life, but we're basically nearing the end of the podcast. We've asked a few questions and had a nice chat with you.
Thank you.
Mhm.
Probably be the end of the podcast then, I guess.
Yeah, thank you.
I have just one last question, if you don't
Sure.
mind, just like quickly. What advice do you have for us, just like for uni maths?
So my advice would be practice, practice, practice. So Really take the opportunity to find as many resources as you can, whether that's STEP, MAT, or even BMO, and just practice those sorts of problems. The thing that people find difficult is the best way of studying maths is sitting down with a problem for 2 hours and not being able to solve it. It may seem like horrible at first. You get used to the feeling, but really not just sitting down with a problem and sort of zoning out, but really trying actively to think about what you've done, what you can do, your understanding of the question, really having that active mindset and practicing lots together will just over time build up. And I guarantee you, perhaps you might have noticed this as you prepared more for certain exams like the MAT or STEP, you'll notice how much easier you find all the other stuff you do, whether that's A level and things like that. And it does follow that the more experience you have, the quicker you see these sorts of tricks, and the more just sort of you can deal with problems with just more ease, and particularly the more menial parts. Even
May probably an Oxford student on probably compare the Cambridge and Oxford student life, and that's I guess it for the
Yeah,
Poincare's
thank you for
Insights
your advice, I
episode
guess.
2.
But
See you
yeah,
guys next week.
I'm really
Bye.
excited
yeah,
to
no,
go.
no
Thank
problem.
you.
Thank you. Best of luck.
Thank you. Thank you.
I guess this will be the end of the podcast.